Have you ever looked at a pressure cooker sitting on a kitchen stove and wondered what magic is actually happening inside that thick metal vessel? To most people, it looks like a sturdy pot with a heavy, locked lid and a small metal weight on top that occasionally whistles, sputters, and releases bursts of intense steam. Yet inside that sealed environment lies a fascinating demonstration of fundamental physics and thermodynamic principles working together to transform tough, slow-cooking ingredients into tender, delicious meals in a fraction of the standard time. By taking a look at a cutaway view of a pressure cooker, we can uncover the exact mechanical process that occurs from the moment you turn on the burner to the moment your food is perfectly cooked. To understand how a pressure cooker operates, we first have to examine the basic relationship between water, heat, and atmospheric pressure. In an open pot, when you heat water, its temperature rises until it reaches its normal boiling point, which is 212 degrees Fahrenheit or 100 degrees Celsius at sea level. At this specific temperature, liquid water turns into vapor, creating steam that freely escapes into the surrounding room. No matter how high you turn up the flame on an open pot, the temperature of the liquid water will never exceed 212 degrees Fahrenheit because all the additional thermal energy simply goes into converting water into steam. This creates an upper speed limit on standard boiling and steaming methods. This is where the engineering of a pressure cooker changes the game entirely. When you place water and vegetables or meat into a pressure cooker and clamp down the lid, you create an airtight seal using a rubber or silicone gasket. As the heat source underneath begins to boil the water inside, steam is produced just like in a standard pot. However, because the lid is tightly sealed, that steam has nowhere to go. It becomes trapped in the small airspace above the liquid. As more and more water evaporates into steam, the gas molecules are compressed tightly within the fixed volume of the metal pot. This dramatic buildup of trapped vapor creates high internal pressure. According to physical laws, as the ambient pressure pushing down on a liquid increases, the boiling point of that liquid also rises. Inside a sealed pressure cooker operating at standard high pressure, the atmospheric pressure inside reaches roughly 15 pounds per square inch above normal atmospheric pressure. This elevated pressure forces the boiling point of water up to around 250 degrees Fahrenheit, or about 120 degrees Celsius. This increased temperature is the real secret behind the incredible speed of pressure cooking. Cooking is ultimately a series of chemical reactions where heat breaks down tough fibers, softens starches, dissolves collagen in meats, and cooks food thoroughly. Because chemical reactions happen significantly faster at higher temperatures, cooking food at 250 degrees Fahrenheit instead of 212 degrees Fahrenheit can reduce total cooking times by up to 70%. Tough cuts of meat that would normally require 4 hours of low and slow braising in an oven can become tender and succulent in less than an hour inside a pressure cooker. Vegetables cook in mere minutes while retaining vibrant colors and nutrients that might otherwise leach out during prolonged boiling. Looking closely at the internal anatomy shown in the cross-section, several critical components work in harmony to control this high-pressure environment safely and precisely. At the bottom of the pot, liquid water sits directly over the heat source, surrounding vegetables like carrots, broccoli, and cauliflower. As the water boils, energetic bubbles rise to the surface, continuously releasing steam into the upper chamber. This rising steam fills every cubic inch of space inside the pot, surrounding the ingredients from every angle. Because steam conducts thermal energy far more efficiently than dry air, heat penetrates deep into the core of the food rapidly and evenly. Positioned directly in the center of the lid is a vital assembly consisting of the vent tube and the pressure regulator. The vent tube is a hollow vertical shaft that acts as the primary escape route for internal vapor. Sitting directly atop the vent tube is the pressure regulator, often referred to as the weight or the jiggler. This heavy, precision-engineered metal weight rests on top of the vent tube opening, sealing it off while the pressure builds. As the steam inside reaches the target operating pressure, the force of the compressed vapor pushing upward equals the downward gravitational force of the weighted regulator. When the internal pressure exceeds this limit, it lifts the weight slightly off its seat, allowing a small controlled burst of steam to escape with a characteristic whistling or hissing sound. This gentle release lowers the internal pressure back to the safe operating threshold, causing the weight to settle back down. This continuous balancing act ensures that the pressure inside remains completely stable throughout the entire cooking process without rising to unsafe levels. In addition to the main vent shaft, modern pressure cookers feature specialized internal baffling and secondary safety vents. In the cutaway, you can see how steam circulates around internal trays and racks. This design keeps food slightly elevated above the liquid if desired, allowing it to steam under high pressure rather than boil directly in water. This preserves delicate textures and prevents food from becoming waterlogged. Furthermore, because the entire system is sealed, virtually no moisture or flavor compounds escape during the cooking process. The concentrated steam infuses deep flavors back into the food while preserving natural juices, resulting in meals that are exceptionally flavorful and moist. Ultimately, a pressure cooker is a brilliant application of basic physical laws combined with smart mechanical engineering. By trapping steam to elevate internal pressure, raising the boiling point of water, and maintaining precise control through a weighted pressure regulator and vent tube, it drastically speeds up cooking times while conserving energy and enhancing flavors. Understanding these internal mechanisms transforms a seemingly complex appliance into a simple, reliable tool that brings science directly to the dinner table.